Welcome to Kvaser AirBridge Lite HS Performance, Lesson 3. Looking at wireless communication protocols, common protocols for wireless communication are Wi-Fi and Bluetooth. With Wi-Fi, it is possible to connect several units or users to the same access point, but not control the latency. With Bluetooth, it's possible to connect several units or users to each other, but it is not possible to control the latency, and the connection range is usually low. The Kvaser AirBridge has developed its own proprietary protocol. AirBridge splits one system into two parts with very low latency and powerful range. The developed protocol of the Kvaser AirBridge is based on 2.4 GHz Gaussian frequency shift keying with frequency hopping spread spectrum modulation. This gives it the advantage that the latency can be controlled. It is approximately 4.8 milliseconds. When compared to Bluetooth, the Kvaser AirBridge has better connection range. It can work up to 70 meters, transmits at close to maximum power, 18 dBm, with internal antennas. The units are delivered in pairs. Several pairs can coexist in the same vicinity without interfering with each other. Error frames and arbitration information are not transmitted by the AirBridge units across the wireless link. Determining the range of a wireless connection is not an exact science, regardless if it is Wi-Fi, Bluetooth, Kvaser AirBridge, or some other wireless connection. There are many factors that might affect the connection. The Kvaser AirBridge utilizes the same frequency as Wi-Fi and Bluetooth, 2.4 GHz. The number of other wireless users using the same frequency within the vicinity of the AirBridge's operating environment will affect performance. The less units in the vicinity that have a wireless connection at that frequency, the better the AirBridge will work. In order to determine what the wireless connection range is for your application, it is best to test it in the actual environment. The Kvaser AirBridge Lite HS consists of two units and is a wireless supplement to a cable connection. As long as the two units are connected to their respective power supplies, they will automatically pair to each other. The AirBridge functions optimally as long as the two paired units have line of sight and are within 70 meters of each other. The wireless signal that travels between the two AirBridge units can be absorbed or attenuated by different materials and environments. Some examples of materials that will absorb the signals are walls, trees, dirt, water, metals, for example, a car door, and concrete. Atmospheric conditions affect the way which wireless signals travel through the air. Lower humidity is better for the connection range, and the amount of wireless users in the vicinity affect the connection as well. The more that obstructs the line of sight of the AirBridge, the lower the connection range will be. Determining the connection range of any wireless connection is not an exact science, since the environment is dynamic and the climate may affect it as well. Higher humidity attenuates the signal more than a lower one. If the wireless signal between the two AirBridge units is absorbed or attenuated, the connection might not work or it might reduce the connection range. The AirBridge units are weatherproof and work better if the antenna part of the units are not encapsulated when they are installed. The AirBridge units are not meant to be submerged or used for wireless communication underwater. Let's look at a connection example. Beneath the steering wheel in cars is an OBD2 port that connects to the CAN network. If you connect one of the AirBridge units to that connector, using a DB9 to OBD2 adapter cable for example, the AirBridge will function correctly when the other unit is within the same car. If you take the other device outside the car, the wireless signal will be absorbed by the metal in the car body and the wireless connection may not work. This brings us to path loss. As a wireless signal moves further away from its source, the signal strength is reduced. A doubling of the distance traveled means that 1/4 of the signal strength is left. When the signal strength is reduced, the wireless connection range is reduced as well. Multipath propagation. The transmitted signal itself may cause interference. It may bounce off of, for example, walls and buildings in the environment and reach the receiving antenna from a different angle and at a different time than the direct signal. This means that the receiver receives the same signal through different paths, and the scenario is illustrated in the figure below. Multipath propagation may either be constructive or destructive for the wireless connection. If the performance of the wireless connection is sometimes reduced, multipath propagation might be one reason. Let's summarize the wireless CAN bridge. The wireless connection range is up to 70 meters, supports both CAN 2.0A and CAN 2.0B, It has automatic baud rate detection at 125K, 250K, 500K, and 1 megabit per second bit rates. And as with any other wireless connection, you do not want to obstruct the line of sight between the antennas, as this will affect the connection range. Note, airframes and arbitration information are not communicated through the AirBridge's wireless link. Let's take a look at a few more examples. In example 1, we look at bridging a single CAN network. The AirBridge units allow a single CAN network to be split into 2 CAN networks and bridged together. In this example, we have one CAN bus with one system for remote control with some example nodes such as engine throttle and steering, and a different part of the CAN bus with nodes engine control and power steering. If we break the cable in the middle and install AirBridge, we create a wireless connection between the two parts of the CAN network. Because we started with one CAN network, for example, let's say it was operating at 500K baud rate, both networks are communicating over AirBridge and both operating at 500K baud. Let's take a look at a second example, bridging 2 different CAN networks. The AirBridge units allow 2 CAN networks, even operating at different baud rates, to be bridged and to communicate. In this example, we have an automotive powertrain with a few example nodes of engine throttle and steering. We'll call that CAN network 1. And then a second CAN network with a second CAN network called automotive battery system with several sensors on it. We'll call that CAN network 2. An AirBridge can be installed to connect these 2 CAN networks together. It's possible to join them even though they may be functioning at different baud rates. If automotive powertrain is at 250K and automotive battery system is at 500K, the AirBridge units will automatically detect those different baud rates but establish a connection and create a unified CAN network anyway. Note, in both example 1 and example 2, airframes and arbitration information are not communicated across the wireless link by the AirBridge units. Let's wrap up by looking at a few case studies. In one case study, a major diesel truck OEM utilized an AirBridge on a test track. The truck being tested was equipped with one AirBridge unit. The other AirBridge was attached to test measurement equipment located on the side of the track in a stationary position. When the truck passed the measurement point, the fast connection pairing of the AirBridge allowed the measurement equipment to capture the relevant data during the drive-by. In a second case study, a large construction crane operator tested using an AirBridge to eliminate the need for cabling on the crane itself. One AirBridge was attached to an electrical network distribution box, which included the CAN bus. The other AirBridge was attached to the monitoring equipment in the crane operator's cabin. The AirBridge eliminated the need for extra cabling. Cabling is often difficult to manage and maintain on a crane due to moving parts in the difficult environment. In the third and final case study, a forklift manufacturer utilized the AirBridge to give mobility to forklifts during the production line and end-of-line testing. One AirBridge was attached to the forklift during the final phase of the production line. The other AirBridge was attached to the test and measurement systems. As the forklift was moved through the final stages of assembly and testing, the AirBridge eliminated the difficulty and maintenance of cabling. This is the end of Lesson 3. For more information on AirBridge Lite HS, visit www.kvaser.com/airbridge or contact us directly at sales@kvaser.com. Thank you.